So now I'm ready to solve my first problem here. Very basic problem, as you can see. We have a function that is just x cubed. It's very simple. It almost doesn't get any simpler. But we have a width of 1 meter and a height of 1 meter. And the question is, what is the centroid location? Actually, this should be x bar and y bar for that area element. So let me fix that. So x bar and y bar. And you pretty much should do that through the integration steps that we just done. So now let's work our way through it. Remember step one. The step one was to show a differential element. So I will do that for you. So I will just draw a random element in here. This is my random element. And I'm going to call this here dA. And really, I'm integrating over dx. So I have my width, which is dx, and my height of that area element is really f of x, which actually is equal to x to the 3. And so remember that our formula was x bar is equal to integration of x tilde dA divided by integration dA. So now what do I have to do? I have to integrate or fulfill those criteria here. And I already found that dA, where do I write it here? dA is equal to x cubed dx. And again, this is the height. And this is the base. Base times height. Now, what is my x tilde for that particular area element? Remember that now I expressed dA in terms of dx. So this was my step number 2. My step number 2 is pretty much done here. My step number 3 was determine the centroid location. So I have to define, hey, where's the centroid location of this? And it's a rectangular element. So it's exactly in the middle here. And what that means is that I have a x tilde for this element and for any other element that is equal to x, right? So even if I move my area element, this area element here, if I move this further to the left, then I would still integrate at x. And so this is true for no matter where my area element is. And therefore, I can now say that my equation up here is actually equal to x multiplied by x to the 3 times dx. And of course, the whole thing integrated. And last but not least, I need to integrate the entire area, or I need to find the entire area, and that's just x3 dx. And all that's left to do for me now is use integration constants. So I'm going to write that down here on the bottom again. So my x bar is equal to x to the 4 dx, and the whole thing integrated, divided over x3 dx. So just to be clear here, I have power 4 because I have the double x here, and then x to the 3 comes from that. And now I need my integration constants. So I need to do this from 0 to 1 and from 0 to 1. And now all I have to do is integrate this properly. So I'm gonna, if I integrate this, I get 1/5 x to the 5. And I do that from 0 to 1, divided by 1 over 4 x to the 4 from 0 to 1. And when I solve this, I pretty much end up with 1/5. This is a very simple example, divided by 1/4. And that ultimately ends up being 0.8 meters. And the solving here is really not the problem, right? So let me point to it. So everything here is not the problem. Everybody in the class can usually do that part. The question is, how do you derive this equation? And we spent quite some time in this lecture to really get there, starting from the center of gravity all the way down to area elements. And now here I'm actually implementing this. And I hope those 4 steps are clear to you, thanks to what I wrote down up here. But this is really the challenge, how to set up the right equation. Solving this, everybody can usually do. Last but not least, I, of course, even though it's simple to solve it, I should check my result here, right? So, I mean, I'm 100% convinced that this is correct here. But I can also convince myself that for an area that has a length from here to here of 1 meter, that an 0.8 is a good value, right? Because if this was a triangle, by the way, and I'm gonna put that in here just for fun, and so you know how I think of these problems. So if I had a triangle, then I would exactly know how large my x bar would have been. It would have been exactly 0.66, right? Or like 2/3, if you will. And now, in this case, I'm actually carving out a component. That means the material gets heavier on the right side relative to where it was when it was a triangle. And therefore, it needs to be larger than 0.66, which is the case. Also, it cannot be larger than 1, and that is also the case. So I solved this. So that's fairly straightforward. So I solved for x bar. Now it's time to solve y bar. I encourage you to do this and pause the video for a second. But I will move on and solve it for you. So what is y bar again? Y bar is equal to y tilde dA divided by dA. And so now the only thing that's different is my y tilde. So let's analyze that real quick. And it's probably best to look at this picture here. What is y tilde? Y tilde is the distance between the centroid location and the origin of the coordinate system. So that would be this distance here. And that would be y tilde, which is equal to 1/2 f of x, which is x to the 3, right? So that is my distance here. And now the rest I can do as before. So I have 1/2 x to the 3 times dA, so which, remember, was nothing else than x to the 3 dx. And my area does not change, right? That's also important to understand, is that the area, of course, cannot change, so it still remains x3 dx. So if I integrate that now, I end up with 1/2 times 1/7. So 1/2 times 1/7 x to the 7. And I integrate that from 0 to 1 as well. And then here nothing changes. In fact, it's 1/4 x to the 4 from 0 to 1. And if I solve this now, I end up with 1/14 divided by 1/4. And ultimately with 0.2857 meters. And so now I need to double check that result as well in my sketch. And in fact, the very last step that I have to do is really look at my sketch, but it was like less than 0.3. And that makes sense as well, right? Because the heavy side of this, what used to be a triangle, is here on the bottom. And so if I carve this part out, it slides more down. And so for a triangle, it would be 1/3, which would be 0.33. But the carving makes it drop further down. And therefore, I'm done. Although the last thing that I really have to do is show in my sketch that I understand where it is. So let's say I pretend it's right there. I need to clearly identify that the distance here would be equal to 0.8. X bar is equal to 0.8 meters. And then last but not least, the distance down here would be Y bar, which we calculated to be 0.285.7 meters. And that is the final answer to the problem. And I believe that is a simple problem to follow. I'm not saying it's simple so that you need to immediately understand it, but it should be understandable once you study it and maybe you play the video a few times. Maybe you got it already. However, this is, I think, a good introductory example that helps you to understand all the components and follow the 4 steps. I'm going to repeat the 4 steps here real quick. So first thing is to find a random element, which I've done here, and then express dA in terms of base times height, which I have done right here. And then you pretty much determine the centroid location, which is this part here, and you define x tilde and y tilde. And then last but not least, you solve your equations using your integration constants. And that concludes this problem, and I will move on to the next one. So in this problem, it becomes a little bit more interesting because we're really dealing with like a structure, if you will. And so let's read the problem statement. There's a structural plate that is made from concrete, which is 2.5 times as dense as water. And it has a thickness of 5/15 meter. That's of course a strange measurement, but that will make our numbers easy. And now you are supposed to determine the support reactions. So just as I explained to you in the beginning of the lecture, when we talked about the homework, what's going on here now? We have a plate that has a centroid, or centroid location. So I'm going to call that C. And there is a force that is going through there. I'm going to call that F plate. And that plate has a distance X bar. And that is what I need to calculate my support reactions, because my support reactions are twofold. I have these guys. I'm going to call this RAY, RAX, and then also I have RBX. And the easiest one to find is RBX. So by taking the sum of the moments about point A, sum of the moments about point A is equal to 0, counterclockwise positive, and 0 is equal to RBX multiplied by the height, which is 2 meters. And then that turns counterclockwise, so I'm going to make that positive. And now I have the F plate multiplied by X bar, and that turns clockwise, so therefore that is negative. And I will be able to solve that equation in just a second for RBX. But before I do that, what I need to do is I need to find how heavy is my plate and what is my X tilde. So let's start with the X tilde because we have done that before, or that's what the lecture is really about. So I need to follow my 4 steps again. I choose a random area element, and I'm going to draw that right here. So I have a random area element. I'm going to call that dA. And dA is really nothing else than base times height. So dx times f of x, which then ultimately turns into, and notice there's a negative, minus 1 over 4 x to the 3 plus 2 times dx. That is my area element. Now I need to identify what is my x tilde. Notice that I don't even worry about the y bar or y tilde. I only need to care about the y tilde. So let me put that in here. So the centroid location of this system would be right here. But I only care about the y direction, sorry, the x direction. So I'm going to care about this component, which is x tilde, which is equal to x once again. So fairly simple in this case. And so I know that my x tilde is equal to x. And now if I write my standard equation for x bar, right? X bar is equal to the summation of x tilde dA divided of all dAs. Now all I have to do is grab my components from here and here. So my x tilde is x. So I'm going to use the red color for that. Or actually, let's change colors here for a second, so it's easier to follow. So x and then times 1/4 x cubed plus 2 dx. And my entire area is just -1/4 x to the cubed plus 2 dx, and of course also integrated. And now it's a question of solving. I need to think about my integration constants. So let me first rearrange everything here. So I have -1/4 x to the 4 plus 2x and all of that dx. And I divide that by still the same thing. But I'm going to do that from 0 to 2. 0 to 2, because I'm integrating over x for that plate here. And if I now rearrange everything, then what do I end up with? I end up with something that is -1/4 times 1/5 x to the 5 plus 2 times 1/2 x to the square, and the whole thing integrated from 0 to 2, and I divide it by the entire area, which happens to be -1/4. Don't forget the negative, that's important, although obviously you cannot have a negative area, but the function here is negative, so that needs to be included. X to the 4 plus 2x. And that also needs to be integrated from 0 to 2. And if I do so, and again, that's not the part here of the class, right? But ultimately you end up with 12/5 divided by 3. And that ultimately ends up to be x bar being 0.8 meters. And that is technically a result, or at least a result within this class, like within the purpose of what this class is about. And so now I solved for my x bar. However, it's not the full result, because remember, now I know that I can fulfill this equation here. And what I know is that this here is 0.8 meters. So the question remains, how do I find F plate? Like, how do I get this one? And the answer is straightforward. It's made from concrete, and I know its thickness, right? So I know its thickness being 2/15 meters, and I know that it's denser than water by 2.5 times. So all I need to do is calculate the area, and then multiply that by the thickness, which gives me the volume. And once I have the volume, then I can multiply it by the density to find its total weight. So let's do that next. So I'm going to do that down here. So F plate is equal to the thickness in meters, by the way, times the area in meters squared, so which is a volume then, multiplied by the density, which usually is called rho. And that is usually in kilograms per cubic meter, but I'm gonna just violate that a little bit and go in kilonewton per cubic meter, because that's what we're ultimate after, like as a force, right? So let's look at that the thickness was 2/15 meters. The area I already calculated, right? So this here is actually the area. So multiplied by 3 meters squared. And then the density of water is 10, or not really the density, the specific weight, 10 kilonewton per cubic meter. And then multiplied by 2.5, because that is the density of concrete. And if I solve this, I will find that my entire plate has a nice weight of 10 kilonewton. And now I can substitute that here. That is equal to 10 kilonewton. And now all I have to do is rearrange this formula, and I'm just going to do that up here because I've written it anyways. So I can say that RBX is equal to 10 kilonewton multiplied by 0.8 meters divided by 2 meters. And when I solve that, I find that my RBX actually happens to be equal to 4 kilonewton. And that is an ultimate result here for this. And of course, solving that is not the problem. But I can include that here now in my picture. So I know that this must be 4 kilonewton. And by the way, notice that for me it came out positive because I assumed already RBX to go to the left side, right? I want to re-emphasize this here. And I also know now for the sum, because of the sum of the forces in the x direction being equal to 0, I also know that RAX is equal to 4. So I know that this is equal to 4, right? And my RAY must be equal to F plate, which therefore is equal to 10 kilonewton. And now I solved exactly what the problem was asking me to do. I found all my support reactions, right? So determine all support reactions for the system. And I have done that based on the shape of the plate and based on its materials. So here's everything in an overview, which I believe should be you should be able to follow it. If not, pause your way through the video and play the parts again that were difficult to understand. And of course, if you have questions, you know how to reach me. But this concludes the real example, something you probably would see in the real world or actually in the exam that you will have for problems like this.